So hello everybody, this is Luboš Pirkl from CFD Support. I am here in our Prague office with my colleague Radek Máca. Hello Radek.
Hello Luboš, good afternoon everybody.
So how are you today?
Yeah, I'm fine, thanks. And how are you?
Oh, I'm also fine, thanks. Are you ready for the webinar?
Yes, I am.
Okay, me too, so let's go.
Yes.
Together with us on the line there is Oliver Felde from CFturbo in Dresden. Hello Oliver.
Hello, Luboš, and good afternoon to everybody.
Okay, hello. The same question to you, Oliver. How are you today?
I'm fine, and I already heard that you are also fine. It's good.
Okay, yeah. So we are. So yeah. So I think we can start. So, hello again, everybody. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design an axial fan from scratch in CFturbo, and then how to simulate and evaluate it in turbomachinery CFD. The webinar is being recorded, and its recording will be available on our YouTube channel. And I hope everything works well, all the techniques is fine, and yeah, in case of any technical problems, feel free to contact us in the future, and we will gladly answer all your questions and comments. Yeah, I'll just last question on to Radek. Radek, is everything okay? Is it working?
Yes, everything is clear.
Okay.
Sound is clear. You can continue.
Okay. Thank you.
Okay.
So let me start with who we are. So I'm gonna introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support. I'm here in our Prague office with my colleague Radek Máca. Radek is our head engineer and senior developer here at CFD Support. And finally, in Dresden, there is Oliver Felde. Oliver is senior manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbomachinery design theory and related algorithms. So this is us. And I would like to say a little bit about the program of today's webinar. So there will be 4 parts in the webinar. In the first part, which is basically this part, will be a general introduction. In the second part, let's call it the design part or CFturbo part, there will be a live example where Oliver is going to introduce CFturbo and a little bit, and then he will show a live example of axial fan design in CFturbo and final export of the designed model to turbomachinery CFD. In the next part of this webinar, let's call it the simulation part or turbomachinery CFD part, there will be the other live example where Radek is going to show you turbomachinery CFD simulation and evaluation of that axial fan exported by Oliver from CFturbo in the previous section or previous part. And in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions to the special window below, or you can even send us an email to info@cfdsupport.com. We will answer all your questions later in this webinar. Feel free to put your questions. This is a really important part. It's your time. We are here for you. So just use your chance. Okay, so which brings me to the design part of this webinar. So I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Thank you, Luboš, for the introductory words. CFturbo is a company based in Germany, and we develop as our main product the conceptual design software CFturbo, which is a modern, powerful, and user-friendly software tool. It can be used for the design of all turbomachinery design components that you can, well, almost all you can think of. It is called conceptual design because you don't start with the definition of data points or by typing in the coordinates, but instead you start with an operational point, and then in the software a lot of algorithms and empirical stuff is used to guide you through a design process, which in the end will give you a good 3D representation of your turbomachinery component. Right now we have 200 active clients globally, and it's still growing. In CFturbo, you have the choice between a couple of different modules. Those modules are those for the design of fan, compressor, pumps, turbine, impellers, both for axial as well as centrifugal machines. But
tu peux baisser un petit peu, je suis sur un webinaire là. Merci. Sorry.
And there are also modules available for the design of vaned stators, plus of course the volutes. Okay, and that's probably quite quickly as an introduction to CFturbo. It's probably interesting for you which industries we serve. So it's basically the aerospace industry, automotive branches, consumer products, energy, oil and gas, and so on. Thank you.
Okay, Oliver. So I'm gonna hand over the presentation to you because I think you're gonna to make the demo right now.
All right. Okay. Can you see my desktop?
Yes, we can.
Okay,
yeah.
Thank you.
Yeah.
Okay, that's the desktop appearance of CFturbo when you started. In the middle, you see a list of available models that are shipped with our software. So this, for instance, would be the centrifugal branch, and here it would be the actual fan branch. But I don't want to go the way over the already designed models, but want to design something completely new. And to this end, I'm entering the ventilator space by clicking on that soft button. And the first thing which is to do is the definition of the design point, because the this conceptual design we perform within CFturbo is a best point design, and the operating point consists of flow rate, pressure difference, and speed. So for that fan, the flow rate is 9,500 cubic meter per hour. By the way, you can at any time customize the unit settings in accordance to your preferences. I choose the SI units for this example. So the pressure difference is something like 3,000 Pascal, and the speed is 4,500 RPMs. And of course, it's necessary to define a fluid. And here air at a temperature of 20 centigrade is used. The total pressure definition is just used for the calculation of some internal average values, but it's not really necessary for the design. Okay, once that is fulfilled, I can press OK, and the first thing is I'm asked by the program what kind of component should be defined and added to the project following the definition of the operating point. And since I want to design an axial machine, it should be an axial impeller. Again, if I choose that options, I'm guided through the design process, and the first design step I'm going to enter is the definition of the main dimensions. The main dimensions are just, if you look at the right, the inlet diameter and outlet diameter of the impeller. But back to the first tab in the main dimension design step. Here, one has to tell whether the impeller should be unshrouded or shrouded. If it's unshrouded, like in our case, a certain tip clearance should be defined. You always get a proposal by CFturbo which can be accepted or which can be overwritten. And in this case, I choose something like 0.5 millimeter. If there was a multi-stage machine, you can also tell about the power partitioning between, for instance, two impellers. So I could have just 50% on the first and the other 50 on the second one. But of course, that should be a single stage machine, and that's why I can stick to that 100%. Also, there are two different design modes implemented. One is the airfoil mode, where aerodynamic properties of airfoils are used to make the design. The other one is a more traditional mean-line approach, where just Euler equation and things like that are used to make the design. So that's kind of a decision you have to make at that point, but as the whole project is fully parameterized, you can also go back at any time and can choose a different design mode. I have airfoil. I want to use airfoil mode. That's why I click that radio button. The next tab holds some parameters that are used to make a good choose of the dimensions. So for instance, the work coefficient can be a design parameter, and this, for instance, is this proposal by CFturbo is taken from the well-known Corday diagram. So we have a specific speed of something like 100 for that operating point, and for that operating point, Corday suggests a work coefficient of 0.6 or something like that. These data which you see here are contained in what we call the approximation functions. Those are shipped with CFturbo, and they are given together with the source where they are taken from. But you can also customize this by just adding your own stuff here, your own functions, which can be, for instance, built in by just copy and paste numbers from, for instance, Excel sheet. And then you can save these things, and you can hold that on your desktop computer, and you can hold it in-house, even if it's very special knowledge. Okay, so that's the work coefficient. Also, there is a diameter ratio to be defined. Again, there is a certain proposal. I'm going to change that to 70%. And there are other parameters given or to be defined, and all of these parameters will be used to get proposals for the main dimensions, as well. Yes, a proposal for the main dimensions. So after I'm happy with the definition of the parameters, I can go to the last tab, can press the calculate button, and then based on balance equations and some empirical stuff, and based on those parameters, CFturbo calculates some proposals, and they look like that. And I want to make them, I want to get rid of these decimal points, and that's why I'm going to change that very last number of the diameters here. Once I'm happy with that, I can just look at the right-hand side in the information panel and can see what are the average values I can expect from that design. So for instance, I can calculate average velocity triangles. I can see with my impeller diameter where I am in the Cordier diagram and what is the meridian contour looking like. Also, there's this automatic checkbox. If I check that and uncheck the automatic fit on the right-hand side, a new calculation of the main dimension is done at any time I change some of these parameters here. Okay, but at the end, when I'm happy with that, I want to, well, I had 70. I want to keep values that's why I take the checkbox off and define something rounded values. And when I press OK, then I get a first no, there's no data. A first guess of my meridional contour. The next design step is the definition of the meridional contour itself within the limitations of the diameter that were just defined. So here I cannot change the diameters itself because they have been designed in a previous design step, but I can change the actual extension. I can directly set it to certain numbers, and I also can change angles of inlet and outlet. And once I'm happy with that, I can press OK, and now I should be able to see something in 3D, and this is given here. Third design step is the definition of the stagger angle and the chord length of the blades at different spans. Also, I have to type in how many numbers I want to have. And because I am here in the airfoil mode, I need to tell him also what kind of profile I'm going to use. And for the reason that our operating point yields or leads us to a so-called high pressure fan, the leap line theory should be chosen to define the blades. And if the leap line theory is chosen, then only the NACA 65 series is available for the blade design. But within the NACA 55 series, there are, of course, a couple of different profiles. So there is a profile manager implemented in CFturbo where you have a certain predefined profiles, but those can be extended by any self-defined profiles or profiles taken from literature, for instance. Okay. Also, what is interesting is at the first tab there is the so-called CU-CM specification. Here, radial equilibrium is used, and that takes is just basically a force balance, an equation for the force balance, and it takes into account again the global setup, the operation point there. Also, the number of blades can be defined here, and the number of spans at which I want to design the blade. I stick to 15 spans because that gives me most of the freedom, and I also will stick to the free vortex distribution of the absolute velocity components right after the trailing edge of the blade. Okay, and because I have chosen already the profile I'm going to use, I can again use CFturbo to calculate what is the stagger angle and what is the chord length at all of these 15 spans. Or if I take off that automatic checkbox, I can just individually define the stagger angle and so on for any of the spans. Okay, that is especially handy if you go into an optimization process, and if you find, for instance, that your first initial design did not get what you wanted to have. So here, then you can scale the profile accordingly, and can try to get closer to what you want to reach with your fan. Okay, once that is finished, I can press OK, and the next design step is then all the 15 profiles at every of that 15 spans is scaled in accordance to the chord length that was defined in the blade properties, and is also staggered with the stagger angle gamma at which was set there. Here I can use the built-in 3D preview. Where are we? Okay, here we are, and you will get an impression what has been done so far. The same can be reached just by go to the 3D model, and you see here what we have reached so far. Of course, when it comes to the design of actual fans, acoustic performance, or well, the acoustic behavior when running the fan is very important, and there is a design step implemented which can be used to improve the acoustic performance, and that's called the blade sweep. And to this end, in two different modes, one can try to sweep the blades in order to get an acoustic benefit. I said two different modes. One mode is sweeping in the meridional view and in tangential direction, and the other one is in the sweep angle lambda direction and in the direction that is perpendicular to that sweep definition. Okay, and if I sweep in lambda, I get an idea of the acoustic benefit I can reach with that sweeping, and I can have this diagram which shows me what is the benefit, especially close to hop and close to shroud in decibel. And you see here, if I zoom in, how the sweeping is performed and what it will mean to the actual 3D shape of the blade. But of course, that doesn't improve the aerodynamic performance of the blade, and that's why there is a sweep correction factor that is automatically computed in dependence on the sweep, and this is something like 0.97. And if I press OK, and I will get this warning here that this 9.7 value is not set in the blade property definition, and that's why I'm going back there, do a recalculation. I get a bit longer chord lengths, and now this is fine, and I don't get any warnings anymore. And in 3D, it looks just like that. Okay, so that's the first thing, and the second one is quite quickly adding a vane stator right behind the actual impeller in order to get the swirl out of the flow behind the impeller. And here I'm just telling him how long the actual extent should be of that bladed fan. Where is the location of the leading and trailing edge? So here, for instance, oh, that was a bit. Let me go back to. I think it's a bit too long. I think it was. It should not be 60, but 45, for instance. Okay, and if I now go back and tell him what is the right position of it, I'm quickly through the design process. Again, I have to enter the blade properties where I tell him how many blades I want to use, what is the general shape of the veins of the stator, and what is the thickness here, because I'm not using airfoil data here as for the impeller design, but what we call a mean line design. Again, I can use the built-in calculation algorithms of CFturbo automatically or just by my own request. And then the leading edge angle will be calculated to get an incident-free flow towards the leading edge, and the trailing edge has to be set in order to get zero swirl right behind the stator. Once that is finished, I'm going to do the mean surface design, and here I go for a certain rep angle that might change from hub to shroud. So I have at the hub, for instance, 7 degrees, at shroud 5 degrees, and again I can get some preview here of the vein or of the blades that have a 0 thickness right now, and in order to get a decent thickness, I'm going to enter the next design step where I define the thickness distribution from leading to trailing edge. I want to leave everything to default, and then the very last design step is to define how is the leading edge shaped. So here, for instance, it had an elliptic shape, and the trailing edge is somehow trimmed with the outlet. And if I press OK and go to the 3D model, I'm ready with my first initial design, which I'm going to save. Of course, test is the right name, and by saving this, I'm coming to the end of that little presentation, and I want to give the presenter to Radek now.
Okay, thank you, Oliver. It was a remarkable presentation and a very nice live demo of CFturbo. So now it's time for Turbomachinery CFD part of this webinar. So I'll take the presentation back. By the way, Radek, can you see my screen now?
Yes, I can.
Okay, thank you.
Yes,
okay, thanks for this confirmation. Okay, so now it's the CFD part. So please let me give a brief description what Turbomachinery CFD is. So Turbomachinery CFD is a unique software developed by Czech company CFD Support. It's a smart and easy to use and affordable CFD simulation tool. Turbomachinery CFD was designed for CFD simulations of all rotating machinery such as pumps, fans, compressors, turbines, turbochargers, hydro turbines, etc. Both radial and axial machines, both compressible and incompressible fluid flows. It is based on OpenFOAM, and we believe Turbomachinery CFD is unique at least for 4 reasons. So the first uniqueness would be Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. What is paid for is the first delivery of turbomachinery CFD and later the technical support and software maintenance. This gives the investment in turbomachinery CFD a permanent value, of course, and also this means our clients can scale their CFD simulations in a really big way. Number two would be turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final results report, for example, it can be run by a single click or by a single command. And all the process is being done automatically. And for this reason, turbomachinery CFD is extremely effective. Number three would be, we believe we deliver the extraordinary technical support. We are proud of it. We keep custom approach to every customer, to every issue. We never leave behind any of our clients. We are very flexible in delivering of technical support. Technical support is unlimited, and we support our clients even in matters out of turbomachinery field, for example, in numerical mathematics, physics, CFD, IT, or even software engineering. The last one is the real tutorials are included in turbomachinery CFD, so the turbomachinery CFD user has no doubts about the best practice settings. The real machines are included that are already preset, and user can basically take one of those tutorials. He can replace the geometry with his own. He can modify the settings and run the simulation. The rest of the workflow is automated anyway, so the requirements of the user skills are quite or very low. There are many other benefits of using turbomachinery CFD. I'm not going to go for all of them. I only finish here with my last point that here at CFD Support, we believe that the future of CFD is the automation. In CFD, everything can be automated. The automation is extremely effective. It's even more effective than we expected in the first place. And nowadays at CFD Support, we only think in automated sense, which brings a huge value to our customers. So everything can be automated. That's our point of view. And now I think this is it from my short introduction to turbomachinery CFD. And now it's time for our live example, which is Radek's turn. So Radek, are you ready?
Yes, I am. So please, can you give me a presentation?
Of course. Yeah. So you can go.
Okay, so I hope you see my screen.
Yes, we do. Yes.
So, okay, so thank you, Luboš, for introduction. And good afternoon again to everybody. This is Radek speaking again. So first, let me briefly introduce the outline of this part of today's webinar. So I am going to show you how easy it is to work with the turbomachinery CFD. So we are going to use the export from CFturbo, which makes workflow even simpler. So as you will see with CFturbo and TCFD, we are able to run a CFD simulation and get significant results just by few clicks. Okay, so we can start. So we simply start from the data which Oliver has just generated and exported. So I can use any file browser, for example, the implicit file browser or file explorer in Windows, but I prefer a commander-like file explorer. So I will go to the Axial file, which is directly generated from CFturbo. Yes, so this is the export from CFturbo. So in the STL directory, there is separate STL files which holds the information about each part of the machine, for example, impeller blades, impeller hub, and so on. And this is basically all what we need to start creating the CFD case and CFD simulation. But in addition, from CFturbo, we get this Axial fun TCFD configuration file, which holds the basic setup for the CFD simulation with our software. So basically it holds the initial condition, boundary condition, and it holds the information about the input geometry. Okay, so for the first computation, there is no need to make any modification. So anything can be run automatically. So to start using TCFD, you need just to click on the configuration file, and the new ParaView session with TCFD setup appears directly. So we have developed the graphical user interface as a part of the ParaView, which is a standard third-party software directly delivered with OpenFlow. So here you are able to set the CFD computation, run the simulation, and post-process the results. So it means that 100% of workflow can be managed directly here via this graphical user interface. So now we can see a standard layout in ParaView where the configuration file is already loaded. So to start using it, we need to just click on Apply to enable this configuration file. And now we can see that the layout is split in two windows. In the first one, we can see the input geometry. So this is the left one, the white one is the rotor part, and the red one is the stator part. And the right window shows the setup of the parameters which is needed for TCFD simulation. So for now, there is parameters which are set, so we can read it, but I think for now it is not important, so I will leave just the input geometry. So as you can see in the left panel, there is a properties panel which has several menus. So I will just undock it and move it a little bit left. Okay, so for example here. And these menus basically contains all parameters which can be changed for the simulation. So as I already said, there is no need to change anything because everything is preset from CFturbo. But I will just go briefly through these menus and tell you what we can change in these menus. So in the first one, the general, here you can save your setup in the TCFD file, or you can load anyone, or reload if you set something in the wrong way and you would like to reload the old setup, and so on. And important parameter, which is the machine type, and it basically choose the type of the machine you would like to simulate, because compressor needs another or different parameters than fan and so on. So you have to set your machine type. In the coordinates, you simply set the axis of the rotation using the point, which is the origin, and the axis of the rotation. The geometry just scales the input. For example, CFturbo use the default unit millimeters and OpenFlow meters, so you have to tell the parameter to scale from input geometry to the meters units. And for example, feature edges includes angle parameters is advanced parameter which can extract the edges from STL and can help the meshing process, which is done by Snappy Hex Mesh. And anytime you point the box with the parameter, you can see the help. So it is really useful, and you can read the information about each parameter. In the physics part, you define the fluid property. So here we have air with the because we are working in incompressible mode. So you should set up the reference density, pressure, and temperature, and dynamic viscosity here. You can choose the turbulent model. So for this case, we have K omega SST. So the menu speed lines includes the simulation points. So here you can change the number of speed lines, for example. So you can in one simulation you can simulate different speed of rotations using the speed lines bar. And for each speed line, you can define several points which holds the information about the boundary condition. So for each point, you have to set the maximum number of iteration for each steady state iteration or for each steady state simulation. So here we have 500 iterations for each point. And as I can see, as I already said, that each point holds the information about the boundary conditions, about the different simulation, and this is set up in the inlet and outlet boundary condition. So for this simulation, we simulate several points with different volumetric flow rate. For another type of simulation, we can set, for example, different total pressures, different directed mass flow rate with the different inlet direction, and so on. And for this type of simulation, where we prescribe a volumetric flow rate at the inlet, so we prescribe the fixed pressure at the outlet boundary condition. And because we are working in incompressible mode, this is the static, this is the kinematic pressure, so the reference pressure is 0 at the outlet, which is a standard approach to these type of simulations. Inside the simulation menu, you can choose the steady state simulation or steady state and transient simulation. If you choose the transient, so you need to define the time period for the computation of each point. So you can define it as the time in which is scaled to the revolutions per point. So it means now the simulation will take 4 real revolution of the wheel, of the rotor, or you can set it just in seconds. So I will leave, for example, these revolutions per point. And important parameter, which is the processor's number. So you can set any number of processor with respect to your machine, to your hardware. So there is no limitation to number. And the scalability is really high. We performed a lot of simulation and studies which proves that the scalability with the increasing number of processor is really high. And for example, you can set the second, the numerical order, second or first. Okay, so this was the simulation menu. In the numerics menu, this menu has relaxation parameters and initial condition. So it holds the value of relaxation parameters for the solver, and initial condition holds the initial value or initial guess for each variable. And then we are coming to the components menu, which is important for definition of the geometry. So if I redistribute the windows, okay. So here the component basically defines the input geometry and the computational mesh, and the strategy for computational mesh construction is really simple, and basically it follows the geometry construction in CFturbo. So each part of the machine, in this case rotor and stator, or other parts for different machine, are defined as one separate component, and each component can be defined both using STLs, and then the mesh is created using the SnappyX mesh, or you can use any external OpenFOAM mesh. It means any external mesh which is converted to OpenFOAM format. So you can also use the external meshes, and then you can define the component name. The software also provides the periodic segment, so if you would like to simulate just one blade from, I guess, 17 blades for this case, so you will define here 17 periodic segments. And afterwards, for each STL, which is connected to these components with this impeller, you define the physical type of the boundary. So for blade is blade, for the inflow, which is really physical inlet to the geometry, is inlet or outlet. and the interfaces between each component. There is interface outlet interface or inlet interface. And for each geometry, in case of STLs, we should define the level of refinement. So refinement for each part of the geometry. We can add the layers to any part of the geometry, usually to the wall, and the communication approach between rotating and the non-rotating part usually. So this simulation uses mixing plane approach, or if you set 0 mixing planes for the interface, then it means it uses arbitrary mesh interface. So this is done for both components, and here you can see a fine figure of your topology. So it is really useful when you start creating your mesh from the scratch. So for example, if I connect it wrong, for example, so you can see the mismatch, and the dashed line shows you that something is wrong. So if I first component should be connected to second, so you can see that everything is okay. The solid arrow shows you that you connect these components correctly, and you can check it here. So it is useful when you create the mesh from really beginning. So other parameters, for example, background mesh size defines the largest cell in the geometry, and internal points inside the component. Yeah, because we would like to mesh the geometry from inside. Okay, and other parameters, other menus are related to the SnappyHex mesh. So it includes parameters which can be set for SnappyHex mesh, but there is the best practice setup for each type of machine. So there is no need to change it or change them. So the last is the post-processing. Here you can, for example, define from which patches you would like to evaluate the efficiencies, pressure drops, and or the torque. So basically you can edit here. The largest averaging window define how many iterations should be used for the averaging of the results, and also for the transient type of simulation. You should also define the transient window in seconds. So, or here for this case, revolution. So the result will be averaged for each one revolution of the wheel, or you can set it in seconds, of course. And snapshot interval, if you would like, for example, generate a lot of images to create, for example, the video, as you can see at the beginning of this webinar. So you can set the snapshot interval here. And the last but not least, you can define user-defined function, which can hold some advanced post-processing or different turbulence model, and so on. Okay, so whenever you are satisfied with the setup, you should click on Apply to apply the changes in the setup. So I will dock it back here on usual position. Okay, yes, perfect. Okay, so this was the setup, yeah. And now we can go for the running of the simulation, and to do that we use this TCFD manager. So I will click on it and click on Apply, and now we will see we can see the new buttons in the left panel. So using this button we can simply run the simulation. So first I can define the directory name in which the results will be stored, for example my case. Then I click on Apply. Then I should write the case, so it creates the important files and directories to run the case. It creates all necessary files and so on. And after that we can run the whole simulation by one click. using this button, or simply we can iterate this process. So first by creating the mesh, so I can click on the mesh all. So now you can see that now it's meshing the component 1. So if I jump a little bit in time, which I hope is somewhere here. Oh yes, yes. So now the mesh is done. I can visualize it. For example, the rotor wheel. So by clicking on the show button and then apply. So here is the mesh. So I can visualize it, see the topology. Okay, so this is the mesh after the meshing. And when I am satisfied, I can simply run the calculation. So during the simulation, you are always informed about the process. As you see at the beginning, the meshing process is shown, and afterwards you can see a progress of the simulation. So now you see that the simulation is starting. We have a lot of points. So now we can see the first point is simulated, is computed, and here you can see the remaining time for the point and for the speed line, because we have defined only one speed line, so it corresponds to the total time left. Anytime we can skip to the next point, abort the calculation, or abort the calculation and write the current result. Anytime during the computation, we can update report, which gives you instant information about the computation. So usually you can follow the residuals, or you can see already computed points. So so when the report is updated, you can see it here in this window. And for example, here are residuals within first 18 iterations. Okay, so when we jump in time again, so now we can see that the run calculation is done. So now we can see the full report with all defined points. So now I will go quickly through the report, which holds the simulation statistics. So it is the name of the case, number of points simulated, which machine type, rotation speed, mesh size, details about mesh, non-orthogonality, and so on. Y plus, important parameter for turbulence modeling for each part of the geometry. Wall clock time, so how long does it take to get the solution, how many processor was used, and so on. And then there are several characteristics. So for example, fan characteristic, which is the important parameter for fans. So for each point, which is defined by the boundary condition, volumetric flow rate. The next one is the efficiency, important parameter. So now you can see where is the best efficiency point. You can clearly read the values from this table, and the convergence process through the computation. Then another parameter is torque, which is automatically evaluated for each point. You can see the convergence again, total pressure difference between inlet and outlet in pascals for each point, so you can clearly see a lot of information, total pressure per interfaces, velocity magnitude per interfaces, circumferential and meridional angle again for each interface. And that is all for this. So this was the report, because we run also the transient report, so you can see here. So here is the transient report. So again, you can compare the result between steady state and transient, the efficiency, and so on. So here you can see the progress, the values during the simulation, and so on. Yeah, so this is nice report with a lot of information inside. But furthermore, you can do your own visualization. So I prepared some of them in advance, so you can clearly visualize the whole geometry with for example, total pressure distribution, or just a part of the geometry, so hub and blades of stator and rotor. You can do any slice as you want. You can align the vector field, for example, to the slice and visualize the glyphs of the relative velocity. It means it automatically computes URL, which is the relative velocity in the rotor part and stator part. And for example, we can also visualize the 3D streamlines along the blades. So this is the standard tool in ParaView, and we have developed also the turbo filters, turbo tools. So for example, this is the example of the meridional average. So it can be applied on every axial symmetric geometries. So it computes the meridional average, and it can be visualized on the reference plane or on the reference meridional slice. The next one is turbo unwrap for blade-to-blade view. So for example, this is the blade-to-blade view for rotor and stator with pressure contours distribution. Or here is the slice at, let's say this is in the middle, so in 50% of radial coordinates between hub and shroud. And on this slice, we can visualize, for example, streamlines with velocity distribution. So basically, there are a lot of possibilities how to visualize what you want. So I think my time is already up. Okay, so at the end, as you have seen, the TCFD is a great, easy to use and powerful tool for detailed evaluation and validation of your geometries. So basically in CFturbo, you can design your machine, and then by a few clicks, even without any deep knowledge of CFD, you are able to validate your geometry. So using CFD for turbo machinery evaluation has never been easier. So I am almost at the end. Okay, so maybe I can.
Yeah.
Luboš is back. Okay.
Can you hear me?
Yes, we can.
Okay. Yeah. So thank you, Radek, for your live demonstration and for the demo. We have had some technical problems, but I think it's gonna be okay right now. Yeah. So I'll take the presentation.
Oh, yeah, sure.
Back to me. Okay. So I believe you can see. Or can you see my screen?
Yes, I see. Yeah, now I see the video.
Okay, yeah. So, yeah, I need to start my presentation again. Yeah. Okay. So, yeah. So this was the live example of turbo machinery CFD, and now it's time for your questions and our answers. So this is the time, so please put your questions and we will go one by one and answer them. Okay, so we already have a few questions. So yeah. So this one is okay. I have one for Oliver. So how is the sweep correction factor in CFturbo calculated? Oliver, you think you can answer this question?
Yes,
or?
yes, I can.
Okay.
The sweep correction factor is a function of the absolute velocity distribution right after the trailing edge of the impeller. It is also a function of the chord length distribution and also a function of the sweep angle distribution. And it is based on an empirical formula with a certain set of coefficients. So yeah, that's the answer. It's an empirical correlation. It doesn't take into account well, the 3D sweeping, but the sweeping into lambda direction.
Okay, thank you, Oliver, for this answer. And yeah, and I see a few questions on Radek regarding turbo machinery CFD. So Radek, can you go for them? Can you already see them, because I have assigned to you as the answerer.
Okay, I see. So I can start from the beginning. Okay, there is a question: how are the values chosen for the boundary condition inlet? Okay, well, so I can find it. Yeah. So I will go, for example, here to the settings menu, inlet. Well, okay. So from the CFturbo export, you get the design point, which holds the. Yeah, thank you,
Yeah.
Bosch. So now you can see my screen. Yeah, I hope.
Yes, we can.
So you get the best design points from the CFturbo. So it depends on the design step. So on which volumetric flow rate, let's say, is the actual fan designs. So basically to validate the best design point or to find the the shape or the real properties with different volumetric flow rates. So you should define as many points as you want to find or to validate the best efficiency point or really the line, the profile of the efficiency with respect to the volumetric flow rate. So it was designed with respect to the design point, and we define a lot of points along or among these points to see nice figures and to see really the characteristic and the properties of this fan for the, let's say, wide range of volumetric flow rates. Yeah, so basically it's up the user which knows the properties of the fans. Yeah, so we set it in this way. So it is up to user. So I hope I answer it.
Okay, very well. And there is also a question, another one. How are the values chosen from the boundary condition at the inlet?
Yeah, it was answered right now.
Yeah.
What is the STL mesh? So how it is different from external open foam meshing? Okay, so if you would like, there is two options how to define the computational mesh. So first one is to use in-house or the Snappy hex mesh tool, which needs the STL files, which is just the surface triangularization. I can show it here. Components, surface with edges, which is the output from CFturbo, and it is just the surface geometry. So if I apply the clip, so I will hope you will see, yeah, it is just really the STL and the surface geometry. And for this, using Snappy hex mesh, we can define the volumetric mesh, which is used for computation. So if you don't have external mesh, you can use it directly this approach. Or if you have the external mesh, you can use it, and simply in the settings, you just loaded the external mesh, and directly here appear the patches or the boundaries from the external mesh, and you assign the type in the same way, but you skip the step of creating the mesh. So the Snappy is automatically skipped and the external mesh is automatically used.
Yeah, okay, so it's another one. Then, yeah, how can we optimize the designs with the help of steady state analysis report? So yeah, if this question is meant on the optimization tools, those are on the way. Those are under the development, and we collaborate extensively with other partners at CFD support. So that's the future, and it's going to be soon introduced. So that's about this. Yeah, another question. Yeah, let's go one by one. So there's another one for Radek. Is there already a way to get a good mesh, including boundary layers, the Snappy hex mesh? From Marcus Koman. Hello, Marcus. Yeah. So, well, Radek, would you answer this?
Yes and no. It depends on your geometry. Yeah, if you, for example, for this axial type of geometries, there is a good result for to get the boundary layers with the Stampix mesh. Problem is for the really complex geometries with high curvature. So for this type of geometries, basically it needs really more time to find the proper parameters to really get the nice boundary layer. Yeah, so for, let's say, for flat and not so curved surface, we can get really nice boundary layers. So for this Axial fan, we are able, or using this software, you are able to create nice boundary layers with, let's say, with the 95, more than 90% of how to say, of success edit, successibly edit boundary layer. So yes, but it needs maybe more user interaction to achieve it. Yeah. So.
Okay, then yeah, let's answer by the answerer, right? So I now I see at least 3 questions where Oliver is going to answer. So will you answer them? The CFturbo on Linux and also the next 2 ones.
Oh yes, I can. There's one question: is CFturbo and TCFD available on Linux? For TCFD, I can say yes. For CFturbo, I have to say it's only available under Windows. So that's
Okay.
probably a limitation. Then there is a question: will it be applicable for the designing of turbochargers in automotive engines? Of course, turbocharger components can be designed in CFturbo and have been designed successfully in CFturbo and have also been analyzed successfully in TCFD. So, and they are used by a couple of customers to this end. What else do we have here?
Yeah. There's also a question. I can answer it. Is it possible to introduce additional geometry upstream and downstream of the impeller, for example, porous media or something? The answer is yes, it can. Yeah, it can be. Any number of components can be added, so it can be really complex. I mean, the model to be simulated. Can we optimize? Yeah. Another question: can we optimize the design of Kaplan and Francis turbine designs? So in terms of can we simulate these? Absolutely yes, you can simulate them in TurboMachine CFD. Yeah, optimization. It was already answered. It's on the way. It's a big topic across the turbomachinery field, and we follow all these trends. And we've already done quite some. Work has been done, so it will be introduced soon. On Radek, is it possible to model a periodic section and introducing mixing planes for the stator components?
Yes, it is possible, and actually I prepared a case because from CFturbo you can also export just a periodic segment. So if you you still see my screen? Yeah, okay.
Yes, we can. Yeah, go ahead.
So this is the input geometry. So this is really only one section. As you can see from the settings, there is just a change that where is the components? So basically here you define the number of periodic segments, and the mixing planes are defined here in this column. So here for the communication between stator and rotor part, the 10 radial mixing plane is used for communication. And yeah, in this case, there is no way how to create the AMI interface. So yes, it uses the periodic segment uses mixing plane approach, and the number of mixing planes are defined here. Yeah, so it is available, and we are also about to introduce for, let's say, the communication for unsteady state, for transient cases, the special boundary condition which can handle also the transient cases for the segment parts. So I believe it will be available in the next release. So also this will come in few months.
Okay, thank you, Eric, for this. So, and another question on you. My question is about processor and simulation. What is the physical meaning of the processor numbers, and what happened if I set the very high number or very low number, for example? Yeah.
Okay, well, it depends on a lot of parameters. So, in general, you can set any number. So, but it is I would say it is where it is simulation. Yeah, it depends on your hardware. So if you have just 100 cores, so there is no way why you should set 200 cores. You can, but it slows the computation. So there is no reason to do that. Then it depends on the cell numbers on your mesh. If you have just a coarse mesh, so there is no need to compute it on 100 processors. Yeah, so because the scalability increases. But if you have, let's say, 20 million cells in your mesh, then there is a good reason to use 60 cores, 100 cores. Yeah, so it depends on the mesh and on your hardware. So restriction for the hardware, use just the number of processors you have, and there is no reason to use 100 processors to simulate the mesh, which has just hundreds of thousands of cells.
Okay, the next question, what or if any optimization tools are compatible with TCFD and e.g. OptiSlang? Question from Alistair. Yeah, the same answer as before. We are now in the early phase of our research on let's say optimization tools partners, and OptiSlang is one of them. So we are currently in the let's say merging process. So let's see. We are going to we are working on it. Let's say. Okay. Yeah. I noticed that in the simulation looks like velocity pressure limiters. So Radek, would you answer the top question?
Oh yeah, I am. Yeah. We can see it right here. So yeah, it is included. There are limiters for the pressure and velocities, and it is included directly into the solver, which helps to converge the solver. So basically, it helps at the beginning of the iteration when your initial conditions are rough or not so or are far from the results. So yeah, it is directly implemented in the solver, and it helps to the solver. It is just a convergence. Yeah.
Okay.
You have the convergence. Yeah.
Okay. Yeah. How can we measure the quality of mesh? Again on Radek.
Okay. So basically, you can see it here in this report, and the measurement, the mesh size, and details are here. So it follows the common parameters which must be satisfied with every commercial solver used finite volume methods, so that it's cell volume, for example, skewness, non-orthogonality, which needs to be less than 70 or at least at 80, and if it's more than 80, it is not so good to use it, because you can see the divergence and so on. Well, the skewness, the open form, or our solvers are quite robust with respect to the skewness, so skewness is not a big deal for the solvers, and other parameters are the same for for these common parameters which should satisfy some values. There is no, I think here is no time to to discuss all of them. So if you have questions, so write to our email addresses, and we will discuss it with you directly.
Okay, so the quality of the mesh, yeah. The next question, an example of engine combustion. Yeah, there is not yet a combustion module in TurboMachinery CFD, so no combustion yet. And also another question, can we use it for fuel optimization of engines? Yes, you can. It's general CFD. Can we measure level of the noise? Yeah, aeroacoustics is another big topic across the CFD of turbomachinery. We are developing a new module which is going to be introduced quite soon. I believe it will be still this year. That's my expectation. Yeah, and then we have a couple of questions regarding CF Turbo or turbomachinery design. So Oliver, are you still?
Yes,
Okay.
Yeah. What is the next CFturbo question?
I will read you the questions. So the first one is, will it be applicable for designing low blade number ducted fans and counter-rotating ducted fans?
All right. Okay. Counter-rotating fans. The design of them will be available with the next major release in coming this year, and low pressure as well as low number bladed fans can be designed with CFturbo even today. So the answer is yes.
Okay. The next one, again on Oliver, can we solve fan without direction blades?
I'm not sure whether I understand it correctly, but I can tell that almost any kind of geometry what you have in mind for this design of blades can be considered within CFturbo.
Yeah. It's like without stutter, for example, meant.
Yes, of course.
Of course, yes. Okay, yes, of course. Can we predict combustion parameters through CFD turbo?
Well, combustion parameters can't be predicted or calculated with CFturbo because it's a design software. Of course, it does perform a couple of calculations and so on, but it's not meant to design, for instance, combustion chambers and so on, where combustion plays a decisive role.
Yeah. So it was this. The next one is, can we use CFturbo for the energy audit analyze in the turbomachinery?
Yeah, the answer is similar. As we do a lot of calculations about averaged values, there is, of course, some sort of an answer of CFturbo towards the performance behavior of the machine that has been designed, or the turbo machinery that has been designed. But this is only true within the accuracy of that kind of calculations. And those kinds of calculations, of course, have not the accuracy as TCFD or CFD in general would have.
Okay, so it was this question. Yeah, the next one is, can we use the CFturbo for the analysis of the cavitation problems in the pump?
It's similar. If you want to analyze the problems, then you should use a CFD package like TCFD. But of course, if you want to design something what is not crucial to cavitation, then there are some guidance given, or guidance in choosing the right parameters towards to have a design which is not prone to cavitation, or where the cavitation is a lesser problem than with a general design. So
Yeah.
you will be helped through the design process, but it's not an analysis tool.
Yeah, of course. So it's this, and the second last question is on Radek. Can we vary the temperature of the flow as it passes through a multi-stage simulation?
So I don't know if I understand it well, but basically if we compute it in the compressible mode, so yes, you can, with compressible simulation, we have the temperature field, so we can see the temperature drop through the passes, through the multi-stage simulation. So multi-stage can be also simulated here. So, and for high velocity or high pressure fans, compressors, so there is compressible solver, even transient, but also transonic solver. So I believe yes, it is possible if I understand the question correctly.
Okay. So and there's this will be last. Okay, we have few more, but I think we should finish. So the last question and answer is, how can we get this recorded video? Yeah, there will be an email sent to all of you where the video will be uploaded. So don't worry, we will send you the email on this. Yeah, and I think this is it. Let's finish. So I will get the information, back, the presentation back to me. Okay. So yeah, I think it's time to conclude. So thank you for coming to the webinar. Feel free to contact us in the future. I'm sure you know very well how to do that. The questions on CFturbo are to be sent to CFturbo company. The questions about turbomachinery CFD are about to be sent to CFD support. We will gladly answer all your questions and comments. We will gladly support you in your turbomachinery projects. It's our job and also a pleasure for us. Yeah, so anything more to say? Oliver, would you conclude?
No, I just want to thank to the audience for their time, and I hope I can answer a couple of questions more or can get into discussion with you. Thank you.
And Radek?
Also, I'd like to thank you, the audience, and yeah, I really believe that the software and the synergy of CFturbo and our TCFD is really the future of turbomachinery virtual prototyping and can save a lot of time in this process of the virtual prototyping. Okay, thank you.
All right, so we would like to thank you all for the attention. We are looking forward to collaborating with you, so stay tuned and bye-bye for now. Bye-bye.
Okay, bye-bye.
Bye.
Yeah, bye-bye. Yeah. Okay, so this is it.